So let's start. Any doubts in the contents of the previous weeks or the assignments of the weeks that you have done till now? Okay, if not, then we can proceed to the content that we will discuss today. So, up till now, again, just to summarize, what we have seen is the kinematics of manipulators, and we also discussed the static force and moment analysis and how they propagate in manipulators. So now and we are at a stage where we can move on to the discussion of dynamics of manipulators. So just a very basic brief on terminologies. So kinematics means studying about motion without discussing about what's the agent causing the motion, right? The reason behind the motion. That's kinematics, which we have seen right now, right? We have talked about velocities, angular velocities, but we are not worried what's the agent or the source creating those velocities and how they're affecting the motion of the manipulator, right? In dynamics, we study about the cause of the motion, right? So what's the uh, agency is a term which is being used, which is causing the motion of the body or the manipulator in this case, right? So the agency can be either a force or a moment or both of them acting simultaneously, right? So today, what we will discuss is uh, how do we compute the dynamics of manipulators, how do we compute the required joint torques uh, in order to move in a certain way, and we will solve few questions around that. Okay, so let us begin. I will just mark these figures because I will refer to them down below. So these figures are taken from the book which I usually refer to. That's J.J. Craig's Introduction to Robotics. Intro to Robotics, right? So if you would remember, we had seen velocity propagation in, I think, discussion hour 4, right? So velocity propagation dealt with computing the computing the velocity of each link frame and its angular velocity as we move from one link to another link, right? So we found out a relation, a recursive relation between the velocity of, let's say, the ith link to the I plus 1th link, and similarly the angular velocity of the ith link and the I plus 1th link. So I will just rewrite those expressions. So first, what's the angular velocity relation? And while writing, I will also just describe each term so that your memory is refreshed. So the notations are the same which I have been using In case of any doubts, if you still have or are not yet familiar with this notations, you can let me know. Right. So the angular velocity of I plus 1th link is the summation of the angular velocity of the previous link and the joint rate of that joint, right? And all this, since this is a frame uh, dependent form of the equation, so each of the term in this equation is written or expressed in I plus 1th frame. So angular velocity of I plus 1th joint expressed in I plus 1th frame is equal to angular velocity of the ith joint in the ith frame, and that vector is being rotated using a rotation matrix into I plus 1th frame. So this is a transformation, the rotation matrix, plus the joint rate of the I plus 1th joint, which is along the z axis, because we assign z axis along the axis of the joint, right? So along the z axis of the I plus 1th joint. So this is the angular velocity relation. Similarly,
Sir,
yeah,
sir, here, sir,
hmm.
what is the difference between angular velocity and joint velocity, sir? Like they both seem
Yeah,
the same
yeah,
thing.
they are both, they are in fact both the same. I am just uh, impressing or using a different term in order to, you know, separate the two quantities in the way that the joint velocity is just information about that particular joint, right? So joint velocity is of that joint itself, that let's say joint 2 is moving with 2 radian per second, right? And angular velocity, we will say angular velocity of that link, right, which will include summation of all the previous joint velocities, right? We have seen that if first link is moving 2 radian per second, it's a 2-hour planar manipulator. First link is moving, or first joint is moving 2 radian per second, and second joint is moving with 5 radian per second, let's say. So the first angular velocity of the first link is 2 radian per second, and angular velocity of the second link is 2 plus 5, 7 radian per second, right? So just that's the difference. Angular velocity, when I am speaking, I am talking about the angular velocity of the link, which is summation of all the previous joint velocities in the usual only manipulators containing only the revolute joints.
Yes, sir. Yes, sir. Got it.
Yeah. And second is the linear velocity. Let me write it here. So linear velocity equation is, if you would remember, so the velocity of the previous link, previous link frame, plus the velocity due to the rotation of the that link, so omega cross r term, right? So I will write it just like this directly. This So the first term is the velocity of the origin of link I, right? And after that, we have to add the contribution due to angular velocity of link I. So contribution due to angular velocity, and pi is the position vector from origin of the ith frame to the origin of the I plus 1th frame. So the scenario would be something like this, that here is the ith frame, here is the I plus 1th frame, right? And this is the position vector. We choose another color. So this is the position vector which I am denoting as pi plus 1, and this link is going around with omega I. Okay, so and velocity of this frame is vi, velocity of this frame is vi plus 1. Any doubts in this expression? Pretty much straightforward. Okay, so till now we have seen up till here. Today we will also what we'll do is we'll also uh, write equations for accelerations, because in order to work with uh, dynamics and forces and torques, we have to also consider accelerations. So we'll need to see how linear acceleration and angular acceleration is computed for these manipulators. All right, so
Sir,
yeah.
uh, uh, so on this in this topic, sir,
Mm-hmm.
angular velocity,
Mm-hmm.
uh, the for a 3R planar manipulator, sir,
Mm-hmm.
um, the concept says that if it's a 3R manipulator has three joints, right? Joint one, joint two, joint three.
Mm-hmm.
Joint one, sorry, theta one dot is has some angular velocity, and theta two and theta three does not have any angular velocity at the initial stage. Uh, then since because of this since theta 1 dot is not zero, uh, because of that theta 2 dot will have some velocity, no sir. I mean, theta 2 dot will have some angular velocity, no sir, because of theta 1 dot. uh,
So you're saying that
uh,
joint 2 and joint 3 are fixed, right?
uh,
And only
y-
joint 1 is moving.
yes sir, in the initially first initially
Okay.
they're fixed. So we say that because of this theta 1 dot, theta 2 dot and theta 3 dot have angular velocity, right, no sir? That's what we say, no sir. You
No. I will make a small correction here. So what, yeah, so what we, the correct way to say this would be that first joint, so there are three joints, first joint, second joint, and third joint, right? So what we will say that first joint has some non-zero velocity, right? And second and third joints have zero velocities. Zero joint velocity of the second and third joint is zero, right? What is not zero is the angular velocity of the link, right? Because physically those two links are also moving. All right. So that's the difference. Like joint 2 and joint 3 itself are locked. So imagine it would be like, I will just draw the scenario which you described. So let me just put it back into place. So the scenario which you are describing is that there are three links, okay, and only the first joint is moving. It only the first joint has non-zero velocity. First joint. It practically it would mean that you have three motors, one at each joint, and you are only rotating the first motor. Okay, the other two motors are locked, right? So how would this behave practically? This would behave like a one rigid body from here to the end, right? It would behave like that only. Okay, so in this case, what you would say is that this link 2 and link 3 are moving with the same angular velocity as link 1, right? Because there is no additional joint velocity adding being added here. So what you would say is that the joint velocity at 2 and 3, those are 0, but the angular velocity of link 2 and 3, they are not 0, and that is equal to the angular velocity of the first link, which is in turn equal to the joint velocity of the first joint. Okay, so that's the distinction. When I talk about joint velocity, I am just talking individually about that joint. So always think that there would be a motor behind it. So what's this RPM of that motor itself? Only that motor, right? That's what I'm talking. What I mean when I talk about joint velocity of that joint. Okay, what I actually need in computations and all, doing kinematics, dynamics, is the angular velocity of the link, right? So angular velocity of the link is the summation of all the joint velocities up to that link. Yeah, so that's what I said. This is the angular velocity of the I plus 1th link. Is the sum of the angular velocity of the ith link and the joint velocity of the I plus 1th joint. Hmm. Hmm. So previous, yeah, I think you were asking about why you are taking the previous one, right? Yeah, so this previous angular velocity, it contains the information about all the previous joints, right? Because that would be again sum of the previous link angular velocity and the previous joint, right? So it's a kind of a recursive relation. So for let's say for a 3R case, what would you write? That omega 1 will be equal to theta dot 1, just straightforward, because that's the first link, right? So it will move at the same rate, at the same rate at which the motor would be moving, the first motor, right? The second one would be theta 1, sorry, second one would be, I am saying it is omega 1 plus theta 2 dot, okay, and which is equal to theta 1 dot plus theta 2 dot, right? Because if the second joint is also moving, then it's the angular velocity of this plus angular velocity of this, right? So the second link, the second link is being moved by this also, right, and this also. So angular velocity of both these joints or motors will be added, right? And similarly omega 3 will be omega 2 plus theta dot 3, right, which will be equal to again theta 1 dot plus theta 2 dot and theta 3 dot, right? So and so on. Okay. Okay. So and velocity relation also we have. So now the new thing which we will see today is about the acceleration. So linear and angular accelerations. Okay. So linear acceleration, as you would okay, as by the name, is the differentiation of the linear velocity, and angular acceleration is the differentiation of the angular velocity with respect to time, both these quantities. Okay, so when we talk about acceleration, so when do we, just let me know, when do we say that something has a non-zero acceleration, right? When the either the velocity's magnitude is changing or direction is changing or both of them, right? So the point which you have to keep in your mind while differentiating a vector with respect to time to calculate accelerations is that even if the magnitude is not changing, acceleration is possible due to change of the direction, right? Which is what happens when you do uniform circular motion. Okay, so in uniform circular motion, if you are rotating a body with constant angular velocity, the velocity of the mass which is moving in that circle, that is constant. Well, not velocity, the magnitude of the velocity is constant, right? But the velocity is changing the direction, right? And in order to change the direction, there has to be some force, right, which is causing that change in direction. And there is some force which means the force should be accelerating the body, and which is basically the centrifugal force which acts in uniform circular motion, right? So the point I'm trying to make is a very basic and fundamental one, which I believe you all know, but I'm still making it clear because that would answer a lot of questions which you might arise, that how are we differentiating the velocity equation to get the acceleration equation, right? So if we are moving with a constant omega, the omegas here the omegas and everything you consider as vector, right? So a vector quantity, right, a vector quantity has, as you know, two things, right? It has a magnitude and direction. So either both are constant, both are changing, or either of them are changing. So even if one of them is changing, right, then the derivative of that vector, it would be non-zero. Okay, so even if either magnitude or direction of the vector changes, then the differentiation with respect to time is not equal to zero, right? So in this scenario, the uniform circular motion example which I was giving, the velocity vector, the magnitude is omega r, right? R is the radius, right? And its direction is tangential to the radius. So at each instant, its direction is not the same. Its direction is constantly changing, right? And this change cannot happen on its own, right? Because you know from Newton's law that velocity would remain the same if there is no external force. But here velocity vector is not the same. So there has to be an external force. And there is in fact the centrifugal force which acts on it, right? Or the centripetal, whatever you call it. So that's the constant force acting here, which is causing the change in direction. So this very basic idea will be helpful when we differentiate the quantities in the equation for the velocity to get the expression for accelerations, where you would have to note that we would also have to take differentiation and take care of how directions are changing, not only magnitudes, right? Because all these are vector equations. Okay, having made that point, I will first write the expression for uh, the very generic expression for acceleration, and then I will talk about each term and what's the physical reason behind it, and also how do we get it from velocities expression. Okay, so I will use a simpler notation than this. I will just use frame independent notation because writing all this indices everywhere makes things a bit clumsy. So I will write frame independent equations, and they are very easy to comprehend in that form. All right. So first let me set up the frames here about which we are talking. So first, let's say there is the fixed frame or the inertial, which is the inertial coordinate system. Okay, and this is frame O. So always the first thing which we do is set up the inertial coordinate system. Then there is a frame, right? We call it, let's say call the A frame. Okay, and then there is a point P. Okay, all right. So P is the point of interest, and P might be doing a general motion, right? A general motion it might be doing. It might be uh, translating plus rotating, right? So a very general kind of a motion. Trying to remove this cursor. Yeah, better. So P is the point of interest for us, about which we will find the expressions for acceleration and velocity. So the velocity of P, right, and with respect to O. Now this is slightly different notation, so just bear with me. I will make it very much clear. So this is velocity of point P with respect to the inertial coordinate system O, right? I will also I can also, in short, in order to avoid writings with respect to O everywhere, I will write it like this. Okay, so just a notational change. So this is equal to, remember what we had discussed few discussion hours ago, that first we will write the velocity with respect to, so first we will write the velocity of the A frame and velocity of point P in the A frame, right? Does this equation make sense, which I just wrote? That velocity of P with respect to A frame is velocity of A with respect to the inertial and velocity of P with respect to A. That is the velocity of P with respect to the inertial. Okay, so with respect to inertial, this is with respect to inertial, and this is with respect to A frame, right? So the velocity of point P with respect to the inertial, which is a fixed frame, is equal to the velocity of the point P with respect to the A frame and the velocity of A frame itself with respect to the inertial, right? Basic concept of relative velocity. So Vp, which is with respect to inertial, is Va with respect to inertial plus Vpa. Now what is Vpa? Vpa will be what is the rel I will denote the a vector called vrel, which is basically how does this position vector is changing, right? This RPA, right? So VREL plus omega cross the position vector of P in the A frame. Again, this is the same thing which I just wrote here, right? That it's the velocity of the frame itself, right? And the omega cross r term. Here, this VREL term is not there. VREL term is not there in this equation because in this the distance between I and I plus 1, it's not changing. They are 2 points on the same body. So the distance between them is not changing. That's why that term is not present here. So this is the general form, right? That in A, P might be, there will be velocity of P due to its translation and also due to the rotation. Okay, just again, just take a look at this expression for a moment and let me know if there are any doubts. We have done this before, so should not be a difficult thing. Yeah, yeah. So that's why this VREL term is not there, right? Because in frame I, the distance, the position vector to I plus 1, the magnitude of that vector is not changing because those are 2 points on the same body, right? The link is not getting elongated or shortened, right? So the distance is the same between I and I plus 1. So that's why VREL is not there. If I plus 1 would have been, you know, if here is I and here is I plus 1, right? So here I plus 1, in if you look from I plus 1 is just rotating about it, right? It's not moving, translating. Okay. If it would have been moving also, then VREL would have come. Okay. So that's the expression of velocity of point P. Now, now what we do is differentiate it. And here I will spend some time because this is the new thing. And we have to be very much careful while differentiating these quantities. So this is what we are writing. This is the acceleration of point P with respect to ICS. Okay. So this is, I will first write the terms. Again, this VREL, you can, okay, let it be like this only. Okay. So, what is happening? So how does this expression come? So I will draw arrows denoting, what are the relations between. Like differentiating which term in the above equation gives you the terms in the corresponding terms in the equation below. Okay, and differentiating this gives the entire this thing, all the three terms. No, no, no. Wait. So let me give them indices. This is 1, this is 2, and this is 3. Okay, so this is differentiation of 1. I will discuss how do they come. This is differentiation of 2. This will come in differentiation of 3. This will come also in differentiation of 3. And this will come both in differentiation of 2 and 3. That's why you see a coefficient of 2 there. Okay. So this one would be straightforward. That velocity of frame A, differentiate it, get the acceleration of frame A, right? So velocity of frame A and differentiating it will directly get acceleration of frame A, right? Second, relative velocity, that is the velocity of point P in the A frame, right? Differentiating that, we get the acceleration, relative acceleration in frame A. That is also straightforward. The two terms are done. Now, so what's the relation? That relation is d by dt of v rel is a rel. Okay. Now, let's differentiate the third term. Okay. So the third term says is d by dt of omega cross RPA. Okay. So how will you differentiate? We will use the chain rule. Okay. So first will be differentiation of omega, then crossed with RPA, and then it will be differentiation of, sorry, it will be omega cross differentiation of RPA, and finally what there will be is omega cross the term itself which we are differentiating. So why does this term come in? Like you would expect just these two terms here, right? Because this is how you will apply the chain rule, right? But the extra thing which is here is that this frame A is rotating, right? It's a rotating frame. Okay. So what we are doing is we are taking differentiation of a quantity not in a fixed frame but in a rotating frame. Okay. So this is something like that differentiation of some quantity in rotating frame is differentiation of that quantity plus the rotation rate of that frame into that quantity. This term accounts for the change in the direction. You know, what is the contribution to the derivative due to the change in the direction of the frame, right? Because, and I will use this uniform circular motion example here. If you were to see closely, this is in if in it's all in the planar case, this would result in omega square r type of relation, right? Omega square r. And you know that centripetal acceleration is omega square r, right? So this is the centripetal term, you can call it as, right? That this omega r, the velocity, the magnitude is not changing, but its direction is changing. And what's the contribution due to that? That is given by this term. All right. So here the first term would be alpha cross r, right? Which is basically angular acceleration. So angular acceleration into r. This term you would have seen that if angular acceleration is there, then its contribution to acceleration is alpha cross r. The second is omega cross v rel. Okay, because differentiation of this is v rel. And the third is the centrifugal term, which is due to the rotation of the frame. Okay, so this is centrifugal. This is due to angular acceleration, right? And what is this? We will just see. So this term, as I said, also comes when we differentiate VREL. Okay, so differentiation of VREL gives AREL plus omega cross VREL. The reason being the same, right? That you are differentiating VREL in a frame which is rotating. So it there would be a direct differentiation of V and plus with the angular rate of the frame times the quantity which you are differentiating. So the second quantity is due to the reason that the frame in which we are differentiating, or the frame with respect to which VL is defined, that is rotating. Okay, so due to that also there is a change in the direction. Okay, so this term is here also, right? And ARL, as I mentioned, is there. So ARL is here, and since omega cross VRL occurs twice, so this is 2 omega cross VRL, and these two terms is called the Coriolis term, right? So have you heard of Coriolis effect in your geography classes in the school? You would have heard this term, that in when Earth is rotating, the winds which are, the wind streams which are moving in the atmosphere, they get deflected, and they get deflected in opposite directions in the northern hemisphere and the southern hemisphere, right? And that effect you studied as Coriolis effect. So that is precisely due to the same reason. The earth is rotating, and the with respect to it, the winds are moving, right? So there is an additional force which is acting on the uh, those wind streams. This example, there is a very also very insightful video which explains this Coriolis effect. Is that, I guess you might have seen it, I'm not sure. So there is an experiment which some people did to demonstrate this effect, right? So there is a kind of a wheel on which two persons are sitting. So this can rotate, right? And one person is sitting here and one person is sitting here. All right. And initially this is 0. So omega is 0. And they are throwing a ball, right? They are throwing a ball to each other. All right. So they can easily catch it. Very easy, very straightforward. It, A throws to B and B throws to A.
and they can catch it very easily. Now, once omega is non-zero, right? This disk is rotating, all right? Then what you see is that this, uh, if I am drawing the top view, so what happens is that when A throws the ball, so the path of the ball becomes like this, right? And it becomes difficult to catch because the path is now not straight from A to B, it gets deflected, right? This is due to the Coriolis effect, right? So uh, let me just play this also, just to make things clear. Yeah. Can you guys see my screen? You can't see my screen? Okay, I think just got locked out, so I will reshare again. Can you see now? Yeah. So just playing this video to. So this is the first case which I mentioned, right? When omega is not zero. Sorry, zero. The disk is the whatever this wheel is that's not rotating. They can easily catch it, right? And now when you see, it's he's throwing it straight towards the other person, but there is some additional force. So when people observed this initially, they were surprised by this change of direction, right? And to explain, right, because the direction is changing, it means there should be some force acting on it, and right, and then this Coriolis term was sort of discovered. So this is the deflection which I was talking about. Okay, the and this is a rotating frame which you would see. So now the camera is on the rotating frame. You see the deflection here. The path now is curved. So when you analyze with respect to rotating frame, right, this happens. So uh, in order to associate why this is happening in rotating frame, you need to account for it, by adding certain force which takes care of this deviation, because the velocity which that person is giving, right, which you saw here in the rest frame, right, in the rest frame which you saw, that the velocity given by the person is as he's trying to keep it as straight as possible, right? He's trying to throw it as straight as possible. So the velocity from in the inertial frame, the velocity given is the straight line velocity from this person. But when you see the same thing from this rotating frame, see that this deflection happens. Okay, so that's it. And the direction changes when you change the direction of rotation. And with some practice, they are now able to catch the ball. Okay. Pseudo force. Uh, so we avoid. Yeah, I mean the term pseudo force, which gets introduced, in our school days. You can call it something like that, but usually we don't call it as a pseudo force because it's a very ambiguous term. Like it won't it doesn't exactly tell like what is that, because pseudo force you can also you also use it to apply forces whenever you analyze with respect to a non-inertial reference frame, which is what we learn in the you know when we learn mechanics in the school. So yeah, it is, but again, uh, I would prefer you think of it as a, not classify it as a pseudo force. It's a terminology which we prefer not to use. Okay, so what we have now is an expression, a very general expression, right? This expression is the most general expression of acceleration for rigid body mechanics. Okay, and this has five terms, right? So this is commonly known as the five term acceleration. Okay, so one, two, three, four, five terms here. So five term acceleration. So once we are clear with this, we can basically write the uh, expressions. So coming back to manipulators, right? So what I discussed right now is true for any rigid body moving in space. Okay, and what we want to do is write the same thing for manipulators. Uh, we want to write similar relations like this, which we wrote here for manipulators, angular and linear acceleration. So again, I will write the expressions first, and then will be very, you will easily relate those to the five-term acceleration formula which I just wrote. So now I will use the similar notation. So first for angular acceleration of link I plus 1 expressed in the I plus 1th frame. So this will be the angular acceleration of the previous link, right? Rotated in the I plus 1th frame. Then there would be contribution due to the angular acceleration of the and angular velocity of the I plus 1th joint. Okay, so basically this. Okay, so three terms here. And these rotation matrices are just for frame transformation. So don't be much concerned about them. So just note the actual terms which are there, right? This is the first term, right? This is the second term, and this is the third term. So the first term is the angular acceleration of the ith link. Very much clear, right? The last term is the joint acceleration of the I plus 1th joint, right? Theta double dot. The second term, which is in between, is basically the same thing which we did here, omega cross the quantity, right? So basically, the since we are now the theta, differentiating theta dot, right, in a rotating frame, so there would be a direct differentiation which is theta double dot, and also omega times the quantity itself, right, which is what we did here. Direct differentiation ARL and omega times the quantity itself. So here also in the angular velocity expression there was theta dot, we have to differentiate it, direct differentiation theta double dot, and the other component will be omega times the quantity itself, which is theta dot, right? So if you would like to relate this to the velocity expression, the expression which I wrote here, this eraser symbol is distracting me. Uh, Cursor comes. Okay. Oh, let me. So this is this term. Okay. And I'm just writing the same equation, the first equation which I wrote today. So differentiation of this gives the first term here, and differentiation of this term, this theta dot I plus 1, this gives rise to both these terms. Okay, so this equation, two terms here, right? So the first term gives rise to the first term there also. Differentiation of the second term gives rise to the second and third term here. Okay, so one is normal differentiation of this quantity, and the other comes up because the differentiation is in the rotating frame, and the frame in which it is being differentiated is rotating by angular velocity omega I. Okay, so this is how we get the expression for angular acceleration. And if you see the five term formula, so in five term formula you see uh, these quantities. So here we are not separately written angular acceleration, right? So angular acceleration term is already written here very concisely as alpha, but alpha, if you would have to put, let's say, in some equation, it would come out like this. Okay, so again, as I mentioned before also, be very careful. Even if you uh, just see somewhere that the magnitude of omega is not changing, right, it does not mean that angular acceleration will be zero, because the direction of omega might be changing, and that change in direction will be causing non-zero angular acceleration. Okay, just as I mentioned for linear velocity also. So always take care of change in directions also, they also contribute to the acceleration. All right, now the velocity part. So velocity of the origin of the I plus 1th frame, sorry, acceleration of the origin of the I plus 1th frame expressed in the I plus 1th frame is, so this transformation as usual, and inside it is, first will be the alpha r kind of the term. Okay, so this is angular velocity alpha r term which is here, right? Alpha r term which is here, the same thing, plus the, this is the centrifugal term, right? And finally there would be the relative acceleration term. Okay. Hmm. Any doubts in this? Okay, cool. So, and from this equation, we can also easily write what's the, so this is the, this kind of a notation denotes the quantity is about the, or quantity is described for the origin of the frame, right? With this, we give the frames at each joint, right? And this vi plus 1 is the, or v dot I plus 1 is the acceleration of the origin of the I plus 1th frame. But in dynamics, we also need the acceleration of the center of mass because that's what we use in writing the force balance or moment balance equations. So now whenever I write Ci, okay, Ci is the, Ci is the center of mass of link I. Okay, so this would be acceleration of the center of mass of link I expressed in the ith frame, that is the alpha cross r term, and r here would be position vector to the center of mass. Okay, plus the omega cross r term, the centrifugal term, and again the position vector would be not up to the second, or not up to the other joint, but up to the center of mass only. And finally the, this quantity. Okay, so this is center of mass of link I and its acceleration. So now what we have is the recursive relation for angular acceleration and sorry, linear acceleration and angular acceleration, right? And also linear acceleration of the center of mass. And for this, to compute these quantities, we do the outward iteration. Okay, outward iteration. That is, move from the innermost link to the outermost link, from I is equal to whatever, 0 to I is equal to n. So we solve these equations starting from the first link to the final link and calculate these quantities for each of the links. That is the outward iteration. Now, once we know these quantities, the subsequent step that we do is to find the force and torque acting on the center of mass of each link using Newton-Euler equations. So, in classical mechanics, this is basically the all explaining set of equations. Like the fundamental equation in dynamics, classical uh, dynamics, the Newton-Euler equations. And the Newton equations you already are very familiar with. F is equal to ma, right? And a I write as v dot ci, that is acceleration of the center of mass, linear acceleration of center of mass. So this is the linear part. This is the linear part. And of course, since we are talking about rotations also, so there has to be a rotational part also. That is the Euler. So this is Newton's, and Euler gave the rotation part extended because Newton gave the theory for point masses, right? Newton gave all his laws and theories for point masses, right? Euler extended those results for rigid bodies of finite size, right? So, and finite size bodies have rotations. Point masses don't have rotations. Okay. So therein comes the inertia of the body, the inertia matrix or inertia tensor. Okay. So I alpha plus omega cross I omega. Okay. So this is, again, in very general terms, this is tau is equal to I alpha, which you have studied, and there is additional term omega cross I omega. And the first one is F is equal to ma. So just to write them in the more familiar form, the notation sometimes might also confuse. Okay. So any confusions regarding Newton-Euler equations? Okay. So once we have these equations, these Newton-Euler equations, and we have the quantities, right? We have v dot ci for each link after outward iteration. We have this omega dot I, right? And omega I. So we have all these quantities. And inertia matrix we can always calculate, right? We need not, once we know the dimensions and masses and all, we can calculate it. So after outward iteration, we calculate Fi and Ni. So these are the force and torque at center of mass of each link. Okay. So this is one complete part of manipulator dynamics, doing the outward iteration and calculating the forces and torques at center of mass of each link. After this, we do inward iteration. So that is, now we do inward iteration to compute the joint torques, right? Required joint torques, which is our final aim of doing this analysis. Now we do inward iteration, that is from the outermost link to the innermost link to compute joint torques. Okay, so this inward iteration involves force balance and moment balance. Inward iteration involves force and so here I will use this figure, right? So this is the Newton equation which I wrote, right? F is equal to m dot v dot c, right? And here is the Euler equation. N is equal to I omega dot plus omega cross I omega, right? This is about center of mass, right? But what we actually need to calculate is the joint torques because that's the thing which we apply, right? We apply manipulators, we apply joint torques, right? We don't apply forces on center of mass. So in order to generate these kind of forces and torques on center of mass, what is the forces and torques at joints, right? That is what we get in inward iteration. Okay, let me take that figure there. It is this number. Let it be. Let it be. I will copy this. So now note that we have other symbols. So we have other symbols for torques and forces at the joints. So Fi is force on link I by link I minus 1, and Ni is torque on link I by link I minus 1. Okay, so you see Fi and Ni here, which we now know. Okay, since we have done the outward iteration, we know these quantities. Our goal is to now calculate these quantities Fi, small ni, and subsequent for each link. Okay, so now we will just for a given body, right? For a given body, we have to just write force balance and torque balance. Okay, so force balance equation we will write F I I, right? That is the force acting on this link, right? And this Fi plus 1 is the force acting here. So here opposite force will act, right? Like this, minus Fi plus 1. So the net force on this link will be Fi and minus of Fi plus 1. Okay. And I will write everything in the ith frame. So this. Okay, did you get why minus sign is coming? Because this Fi plus 1 is acting on is being acted on by link I on I plus 1. So what is the force acting on I? It will be opposite of that, right? The action force. So this is force balance. And as simple as that, this equation, by solving this equation recursively, we'll get FIs. Okay. And the second one is so this is force balance, right? And this is known. This is known. And since we are doing inward iteration, this is also known, right? And this we compute. And then we go on to the next link. Okay. Now the moment balance will give us. So the torque on center of mass we know. This is the torque at the ith joint, the reaction torque at the I plus 1th joint, right? Then the torque due to since n is for center of mass, so we have to take distance to center of mass, position vector up to center of mass due to force I, and this is on the other side. So basically, what is this? This is four things are acting, right? Four things are there. There is Fi, Ni, and there is Fi plus 1, Ni plus 1, right? So Ni is taken care of. There will be reaction torque due to Ni plus 1, that is taken care of. Like two terms here. What will these forces do? This Fi and Fi plus 1, they will also have some moment around the center of mass, right? So that's what this is. That's what we are writing here, right? This is moment about center of mass due to Fi, and this is moment about center of mass due to Fi plus 1. Okay, and how about the distances? Where these distances taken? So Fi, so Fi, the point of application of Fi is here, and this distance is minus of PCI, right? PCI is from this origin to the center of mass, so negative of that, minus of PCI, and this and Fi plus 1 is acting here, right? Fi plus 1 is acting here, so this distance, let me draw using other color. So this distance, right? And this is what? This is this thing. Okay. So if I draw it again clearly here, this is the link, whatever link is there. Here is the ith frame. Here is the I plus 1th frame. And here is the center of mass frame. Okay. Now, now we define this as PCI, and we define this as, sorry for curved lines, they are vectors, this as pi plus 1. Okay, so these two vectors are the notations we use, the vectors that we use. Here we need first, in the first torque calculation, we need this, the opposite of this vector. So minus PCI, right? And in the second, we need this, that is, we need the difference of the two vectors. So this will be Pi plus 1 minus PCI, right? And this minus sign is due to this same reason the minus sign is here. This is the reaction force. Any doubts here? We have discussed the torque balance. Any doubt in torque balance? Please take a moment and uh, try to see if you have any confusion in the flow of the logic. If you are lost somewhere, please tell me, I will redo it. Force balance you have to do listen again, right? Okay. So imagine what is happening here. Just isolate this body. When you are in confusion, isolate and draw a body, right? This is the link. This is the center of mass. Okay. What we know is that the net force on the center of mass is Fi. How did we get this? We got this by calculating the acceleration of the center of mass. We know the mass of the link, so we know the force at the center of mass. So that is the desired force at the center of mass, right? And that we got after the outward iteration process. So Fi we know. Now this link is being acted upon by two forces from the joints, right? The Fi, right, that is acting here, and the, so basically this is a joint. I'm just, exploding the manipulator, and here the other link is there. So other link, the joint force on the joint I plus 1 is Fi plus 1. So what will the force, so what is Fi plus 1? Fi plus 1 is the force applied on link I plus 1 by I, right? As I mentioned here, Fi is force on link I by link I minus 1. So Fi plus 1 is force on link I plus 1 by link I. But now, since we are analyzing link I here, so we need force on link I. So force on link I will be by Newton's third law, equal and opposite of that, right? So this vector is minus of Fi plus 1, right? So now for link I, right? So there are three forces acting, and force acting on, and the net force should be equal to the force acting on center of mass, right? So Fi should be equal to the small fi and minus of Fi plus 1, right? This, if you write in frame independent form, and this rotation matrix is just a frame transformation. So the concept here is that we know this, in order to balance this, in order to generate the same force which is there on center of mass, what are the forces on the two joints of that link? The forces are Fi and Fi plus 1. This Fi plus 1 is the reaction of the force acting on joint I plus 1, on link I plus 1. Are you clear now? Yeah. So first, you have to be clear that we are analyzing forces on link I, right? The force on link I from this side is Fi, right? And since we are doing inward iteration, we would at this stage of computation we would already know Fi plus 1. Am I right? Did you get, right? You will already know Fi plus 1. And since Fi plus 1 is the force which is by definition the force being applied on link I plus 1 by link I, right? Okay, but for since you are doing now force balance for link I, so you would only write forces in your equation which are acting on link I, right? So on in this side here, what's will be the force which is acting on link I, right? This will be the equal and opposite of force Fi plus 1. Okay, so force Fi plus 1, you will just invert it and add to Fi. So as I mentioned above, in this equation, when you will do invert iteration, this will already be known because you are doing invert. You are moving from n to 0. So this quantity will be known. This quantity will be known from auto iteration and you will get this Fi. Once you know this, you will again move to the link inside that. Okay, so you will next equation which you will write is Fi minus 1 is equal to Fi minus 1 minus Fi, right? In which again you will know this, you just calculate this, right? And this will be known. And similarly you will go till the last link, from the first outermost link to the innermost link. Okay, and the same process will happen once you know all the forces, this FIs. You will also compute the moments. So you will finally what you will do is, so finally we need to have, as I mentioned, we need to have joint torques. So those joint torques are NIs, and since rotation is, we are giving the rotation axis as z, so we'll take dot product of this vector, right, with the z axis. So it will give us the component of this ni vector along the z axis, and that will be the joint torque of the ith joint. So this is joint torque at ith joint, right? So this is the final result which we wanted to have. This is tau I. Okay, so inward iteration is being used here from I is equal to n to I is equal to 1. Okay, and you will get each joint torque. So, and also, like you would think, let's say for a 3R manipulator, which is, because to begin with, right, I said that you have to do inward iteration, right? To start the inward iteration, you would need to know the forces and moments at the end effector, right? At the end effector, you would need to know forces and moments. So if it is free, right, it is not in contact with anything, both of this quantity will be 0. So for the first step of the inward iteration will be very straightforward. This f and n will be 0. Okay, if this is in contact with something, like let's say this is let's say this is manipulator is like this, and it is pushing on something. Okay, this is pushing on something, so then the end effector has some non-zero force or some non-zero moment also. So in that case you will start with that end condition. Okay, so uh, so this is the whole process of solving the Newton-Euler equations, and this is one way of finding the joint torques, right? The second approach, a completely different approach, is what is called as Lagrangian method. So what we discussed now is the Newton-Euler method, which is force-based. The Lagrangian method is energy-based, and For many equations, for many systems, doing analytical analysis is much more convenient with Lagrangian method. So Lagrangian method has its own benefits, as you would see. Both will give you the same result finally. Both will give you the same equation of motion. But in some scenarios, this method might be better suited. So what is this Lagrangian method? So Lagrangian method, the first thing which you should know is that it is energy based, right? So here you would not see us discussing about forces and moments at each joints, right? What it calculates, it what is the kinetic energy of the entire manipulator and the potential energy of the entire manipulator, right? So energy has kinetic energy and potential energy. Okay, so kinetic energy of the manipulator. So kinetic energy of the ith link, right? It is given by half m of that link and vi transpose vi. This is same half mb square and due to rotation half I omega square. So in proper vector and matrix form, it's like this: omega I transpose I omega. Okay. So this is your same equation which you have already studied in school, half mv square plus half I omega square. Okay. So this is the kinetic energy of the ith link. The kinetic energy of the whole manipulator is the sum because this is a scalar quantity, so you can just straight away sum it. This is the kinetic energy of the entire manipulator. Okay. Now potential energy of the manipulator. The potential energy is due to the gravity. So Ui is minus mg and basically dot with the position vector to the center of mass. This is your same mgh written in a more fancy way, a more general way, and some reference value we use to make the potential energy zero at the minimum level. Okay, you can choose the reference as per your wish. Okay, so this is the mgh kind of a term, and that is potential energy. And similarly, since this is a scalar, you can just sum them up. You can sum them up for all links to get the potential energy. Okay, now the Lagrangian, this Lagrangian, which is dependent on the joint angle vector and joint velocity vector, is defined as, it is a quantity defined as the difference of the kinetic energy and the potential energy. Okay, this this quantity is called the Lagrangian of the system. Okay, now there is a whole derivation process of finding the equation of motion using the Lagrangian, but it's out of scope of this course. So I will just write the final result, that is d by dt of partial derivative of the Lagrangian with respect to the joint velocities minus partial derivative of the Lagrangian with respect to the joint angles, and this is equal to the torque vector. joint torques. On the, yeah. So, so this is a very concise way, like the procedure that you will follow here is that you will write the kinetic energy of the manipulator, the potential energy of the manipulator. It will be dependent on joint angles and joint velocities, right? Then you will, for each, so theta I am writing is a joint angle vector here. So let's say for 2 arm manipulator, it will be theta 1 and theta 2, right? And similarly, theta dot will be theta 1 dot and theta 2 dot. Okay, so uh, so what you will do is then just very in a routine way follow this equation, take derivatives, take time derivative, and you will get equations relating the joint torque to the other quantities, basically joint angle, rates, and accelerations. Okay, so this is using this approach. Again, you get the equation of motion, and yeah, this is the energy-based method because in this you will nowhere see the forces and moments. And now the using both these methods, what we get is the equation of motion for this rigid multi-body system, which is a manipulator, right? Equation of motion is something relating forces and accelerations or velocities and positions and all these things. This is the equation of motion, right? Like for a a spring mass system, a spring mass system, the force is F is equal to kx or minus kx. So equation of motion is, let's say it's of unit mass. So equation of motion is x dot is equal to minus kx, right? So something like this. This is the equation of motion, right? So for manipulators, if from both these methods and with some uh, restructuring or simplification, the final equations come out to be like this. So there is a matrix multiplied to the joint accelerations plus there is a vector which is dependent on joint angles and joint velocities, and there is another group of terms, right, like this. So, and this is equal to the joint torques. Okay, so now this first term is n cross n symmetric and positive definite matrix. Symmetric and positive definite, very important properties, very, very important. This is the mass matrix or the joint space inertia matrix. Since we are writing in terms of joint angles, so joint space inertia matrix, right? So this is, you can think of like a m times a term, right? Mass times acceleration term, if you would like to relate to 1D problems, right? Then you have this term. So this term contains all the terms relating to the Coriolis and centrifugal, okay, terms. And this third term is the gravity effect, gravity terms, right? So, and the sum of all these gives you the joint torques. Okay, so this is a n cross 1 vector. N is the number of degree of freedom, number of motors, actuators, right? And this is n cross n, and this is n cross 1, so n cross 1, right? So any rigid body manipulator if you would derive the equation of motion, it can be expressed in this form, right? And this equation, if you study the robotic literature and wherever dynamics or control is there, this equation is always present, and you will see this equation, this form of equation everywhere, right? From whether you study about fixed space arms or you know humanoids or legged robots, wherever you see, this is the form of equation that you get. So any questions at this point? Okay. Okay, so at this point, we have discussed today two approaches to find equation of motion for understanding the dynamics of rigid manipulators. One is the Newton-Euler approach, in which there are two steps. One is outward iteration, that is used to find the accelerations, the linear and angular accelerations, which are used to find the forces and torques on the center of mass. That is the outward iteration step. In the inward iteration step, we use these quantities to find the unknown joint torques. Right. So the outcome of the whole process is the relation between joint torques to the other quantities, that is joint and accelerations, positions, and velocities. Right. Similarly, the same relation can also be arrived upon using the energy-based approach, which is this Lagrangian method, in which we find out the kinetic energy of the entire manipulator, the potential energy of the entire manipulator, then use this equation, the Lagrangian equation, to find relation between the torques and the accelerations, velocities, and positions of the joints, right? And finally, for any rigid multi-body system, the equation of motion can be expressed in this form, in which we have the mass matrix or the joint space inertia matrix, which is a symmetric positive definite matrix. So this is always invertible. Mass matrix is always invertible, right? The other two vectors are the Coriolis and centrifugal term vector and the gravity effect vector, right? So I guess this is a good point to stop, right? And in the next discussion hour, we will see a few questions regarding these concepts, and also I will maybe show the derivation of the equation of motion for a two-hour manipulator. It will be a very quite lengthy, derivation. So I would suggest that you should revise these concepts before the next discussion hour so that we can go smoothly there. Okay. So that's it from my side for this session. We will meet in the next discussion hour.